A viral video claims a slice of buttered bread always lands butter side down because the butter shifts to the center of mass by exactly 2.7 centimeters. You're about to test this with real physics. Your mission, should you choose to accept it, is a 5-stage gamified science challenge. Consider a square slice of bread 11 centimeters on each side and 1.2 centimeters thick, with a mass of 38 grams. It is covered by a uniform slab of butter 2 millimeters thick, with a density of 920 kilograms per cubic meter. The bread is placed on a table 75 centimeters high. It is nudged off the edge with an imperceptibly slow horizontal speed of 0.15 meters per second. The moment the center of mass crosses the table edge, the bread begins to tip and rotates freely as it falls. Air resistance can be ignored. Gravity is 9.81 meters per second squared. Stage 1. Calculate the shift of the center of mass from the geometric center of the bread, caused solely by the butter. Stage 2. Determine the initial angular acceleration of the bread as it starts to pivot about the table edge. Stage 3. Compute the total angle the bread rotates during the 75 centimeter drop, assuming it starts with 0 angular speed. Stage 4. Now imagine that every time the bread is nudged, there is a tiny random initial angular velocity perturbation, uniformly distributed between negative 0.5 radians per second and positive 0.5 radians per second. If the bread must rotate at least 90 degrees but not more than 270 degrees to finish butter side down, calculate the probability that a random release results in a butter side down landing. Stage 5. You earn 200 butter points for getting the center of mass shift correct to within 1 millimeter, 300 points for the angular acceleration, 400 points for the rotation angle, and 500 points for the exact probability. What is your maximum possible score? Here is the full worked solution. Begin with the center of mass shift. The bread volume is 11 times 11 times 1.2, which equals 145.2 cubic centimeters. The bread density is 38 divided by 145.2, giving 0.262 grams per cubic centimeter. The butter volume is 11 times 11 times 0.2, equal to 24.2 cubic centimeters. The butter density is 0.92 grams per cubic centimeter, so the butter mass is 22.264 grams. Total mass is 60.264 grams. Place the origin at the geometric center of the bread. The butter center sits at y equals positive 0.7 centimeters above this center. The bread center is at y equals 0. The vertical coordinate of the combined center of mass is open bracket 38 times 0 plus 22.264 times 0.7 close bracket divided by 60.264. This equals 15.5848 divided by 60.264, which is 0.259 centimeters, or 2.59 millimeters. The viral claim of 2.7 centimeters is wrong by a factor of 10. It is millimeters, not centimeters. Stage 2. Initial angular acceleration. At the tipping instant, the bread is horizontal and the center of mass is 5.5 centimeters horizontally from the table edge. The torque about the edge is the weight multiplied by this horizontal distance. Weight is 60.264 grams in kilograms, 0.060264, times 9.81, times 0.055 meters. This torque equals 0.03254 newton meters. The moment of inertia about the edge uses the parallel axis theorem. The distance from edge to center of mass is the square root of 0.055 squared plus the sum of half the bread thickness, 0.006, and the center of mass shift, 0.00259, all squared. This distance is about 0.05567 meters. The approximate moment of inertia is mass times distance squared, which is 0.060264 times 0.05567 squared, yielding 0.00018666 kilogram meters squared. Adding the center of mass moments of inertia for bread and butter, we get an additional 0.000612, for a total of 0.0002478 kilogram meters squared. Angular acceleration alpha is torque divided by moment of inertia, giving 131.3 radians per second squared. Stage 3. Rotation angle during fall. The time to fall 75 centimeters from rest is the square root of 2 times height divided by g. 2 times 0.75 is 1.5, divided by 9.81 gives 0.1529. Root of that is 0.391 seconds. With 0 initial angular speed, the rotation angle theta is 1/2 alpha t squared. 1/2 of 131.3 is 65.65. Multiplied by 0.1529 gives 10.03 radians. Converted degrees, that is 575 degrees, which means the bread completes more than 1.5 full rotations. Stage 4, probability. The random perturbation omega 0 is uniformly distributed between negative 0.5 and positive 0.5 radians per second. The total rotation becomes theta equals omega 0 times time plus 10.03 radians. Here time is 0.391 seconds. The baseline rotation of 10.03 radians equals 574.7 degrees. Modulo 360 degrees, that is 214.7 degrees. This baseline is already inside the butter-down zone, which spans from 90 to 270 degrees. The perturbation adds an angle shift equal to 0.391 times omega 0 converted to degrees, 22.4 times omega 0 degrees. The perturbation range of omega 0 from negative 0.5 to positive 0.5 adds a shift between negative 11.2 degrees and positive 11.2 degrees. The final angle therefore ranges from 214.7 minus 11.2, which is 203.5 degrees, up to 214.7 plus 11.2, which is 225.9 degrees. The entire range lies comfortably within the 90 to 270 degree butter-down window. Therefore, no matter what random perturbation occurs within the given bounds, the bread always lands butter side down. The probability is exactly 1 or 100%. Stage 5. Butter point scoring. The center of mass shift was 2.59 mm, accurate to within 1 mm, earning 200 points. The angular acceleration was 131.3 radians per second squared, earning 300 points. The rotation angle was 575 degrees, earning 400 points. The probability was correctly found to be 1, earning 500 points. The total possible butter point score is 1,400. This gamified physics investigation shows that while the viral 2.7 cm claim is far off, the combination of table height and rapid angular acceleration makes a butter-down landing almost inevitable under typical breakfast conditions.